Let us now ask ourselves, why does something start to rotate? I apologize for the not so neat handwriting, but anyhow, why does something start to rotate? Well, here, say we have an object um, which is rotating about this rotation axis. So our object is rotating counterclockwise, and for an object to start to rotate or change its rotation, we must have angular acceleration. Angular acceleration alpha. Now, angular acceleration, as we had seen back in chapter 7, is related to the tangential acceleration at via this relationship here, where tangential acceleration at is equal to r alpha, where r is the radius of the circular path. Um, Now, if there is tangential acceleration, that means that there is tangential force Ft acting on the object. So if we have At, which tangential acceleration, that means we must have Ft, and that follows from Newton's second law. If there is acceleration, there is a force that results in that acceleration. So for an object to start rotating or stop rotating or change its rotation, uh, angular acceleration must exist, which implies that tangential acceleration must exist, which in turn implies that there must be a tangential force acting on the object. Now, consider this rod which has a length r, which is pivoted on the left hand side. So this is our, so to speak, our rotation axis. The rotation axis is into the board. So imagine we have a rod and we just drive a nail right through the left end of it into the wall, and that forms our rotation axis, or the pivot point. Now if we apply a force F to the rod, where F makes an angle theta with respect to this linear, or the radial axis, then only the perpendicular component, or the perpendicular component of F will cause rotation. So we're applying a force F, which makes an angle theta with respect to the radial line. That's the word I was trying to remember just a minute ago. Only the perpendicular component of F will give rise to a change in rotation of the rod. In this case, if the rod is stationary, it will cause it to rotate counterclockwise. So let us now define torque, as this is the magnitude of torque, as the product of R with this perpendicular component of the force applied, which is magnitude wise is given as Rf sine theta. Now R in this case is called the moment of arm. So if you have a force F being applied to an object, only the perpendicular component of that force F with respect to the radial line that from the pivot point for the rotation axis gives rise to change in rotation, and the longer this moment of arm is, the larger the value of R is, the more torque one would be applying. So it's really torque that gives rise to angular acceleration, just the way that force gave rise to linear acceleration, is torque that gives rise to angular acceleration. And the longer the moment of arm is, the greater torque you'd be applying given a constant force. So torque leads to angular acceleration. So in analyzing rotational motion, let's say we have our rigid object here, once again the potato. You need to know where your rotation axis is. Once again, the rotation axis in this case is into the board. And let's us say that we have a force F on the right hand side, which is applied at some angle theta with respect to the radial line. Then it's F sine theta, which contributes to change in rotation, and the torque due to F is equal to Rf sine theta. That's the magnitude of torque. Now it is a this torque will cause a counterclockwise rotation, therefore it is a positive torque. Now excuse me, the torque due to F1 on the left hand side is equal to magnitude of the force F1, well, R1 F1 sine, in this case this is a 90 degrees, so sine of 90 degrees, which is 1, so that's R1 F1, and in this case this torque will cause a clockwise rotation, therefore it's a negative torque that we have here. So for each force that is applied to the object, so here we have F2, you need to determine the radial distance from the rotation axis to the object, okay, and figure out the angle that force makes with the radial line, and use the relationship torque is equal to R, or torque I is Ri Fi sine theta I in magnitude, and you need to do this for each and every force that is acting on the object, of course. Now do not forget force due to gravity, the weight, and where gravity acts, we spoke about last time, gravity seems to act at the center of mass. So the force due to gravity, mg, will be, if this is our rotation axis, this black dot on the left hand side, then r naught, which is the moment of arm, for the weight force, is the distance, radial distance from the rotation axis to where the center of gravity is, and the torque due to mg is mg sine theta naught r naught. Now theta naught is the radial, is the angle that mg makes with the radial line, and in this case, the way it's drawn right now, the torque due to mg is a negative torque because it will cause a clockwise rotation. And notice that when the object rotates such that center of mass is directly below the rotation axis, then the angle that mg would make with the radial line would be 0, in which case torque due to mg will equal 0, and the object will come to rest at in that position. So the important thing to remember is that torque is radial distance from where the force is applied to the object to the rotation axis, multiplied, this is magnitude of torque, multiplied by F perpendicular, or F sine theta, where theta is the angle between the two, between the force vector and the radial line. And the longer the moment of arm is, the larger torque one has. So we had tangential, we said that for rotation to happen you need alpha. Alpha implies that you have AT, tangential acceleration, and AT implies that there is some FT at work. Now FT is equal to MAT, Newton's second law. AT we know is equal to R alpha. If you go ahead and put that in, and if I were now to rather than force go with torque, torque we said is R F tangential. F tangential is F perpendicular, so that's my torque. It's equal to M R squared. Now alpha, I just multiplied both sides by R, which gives me torque, magnitude of torque is equal to mr squared alpha. So if we define mr squared as I, which is our moment of inertia, moment of inertia for the object, then we end up with torque is equal to I alpha, which is the analogous equation to F equals ma, Newton's second law, but F equals ma is for translational motion, linear motion, translational, and torque is equal to I alpha applies to rotational motion. Torque and force are analogous entities. One describes rotational motion, the other applies in translational motion. We have mass in translational motion. In rotational motion we talk in terms of moment of inertia. It's not just the mass, but the relative distance of the mass with respect to the rotation axis also plays a role, hence the r squared term here. And in translational motion we have linear acceleration. In rotational motion, of course, we have angular acceleration. So to study the dynamics of rotational motion, we use the rotational equivalent, Newton's second law, which is tau equals I alpha, or torque is equal to moment of inertia times angular acceleration. So once again, you can rewrite this equation in the more familiar forms. We had A is equal to F net over M. So if you have a net force acting on an object which has a mass m, you end up with an acceleration A. Similarly, if you have a net torque acting on an object, and if you know what the moment of inertia of the object is, you will then be able to calculate alpha, angular acceleration. So net torque gives rise to angular acceleration just the same way that net force gave rise to linear acceleration. And this net torque you calculate by, if I scroll up here, by calculating each individual torque due to each individual force that is acting on the object. And please do not forget weight, mg, which you'll always have to consider. So all the forces plus mg, the weight, will be acting on our object. So you will have to determine each respective radial distance from the rotation axis, and if you know each respective angle, then you can calculate each individual torque. If the torque acting on its own would cause a clockwise rotation, then it's a negative torque. If it's a counterclockwise rotation, it's a positive torque. And then you calculate the net torque by simply summing up all the torques, and this net torque is what gives rise to angular acceleration, because net torque divided by a moment of inertia is equal to angular acceleration.